the AC impedance spectrum. Let me just make a quick review of what we have done last time. Okay. Last time we have three types of electrochemical cell. The first one was a symmetrical cell, and that is M, X, and M. And we can have a circuit analogy for this is the resistance. And the second one is ionically locking electrode. And that is M, MX, and P, and corresponding electrical circuit is going to be the bulk resistance and double layer capacitance and the geometric capacitance, CG here. And CI is much greater than the CG typically, okay? CI is much greater than the CG. And the third type is mixed conductor. A cathode. And both electrons and ions conducting. MXY as a cathode. So the electrochemical cell is going to look like this, and the circuit analogy is going to be the resistance for the bulk resistance. And now in this case we are going to have a double layer capacitance and Warburg impedance in parallel, and we have geometric capacitance like this. Here the Warburg impedance. That is related to the chemical diffusion of neutral atoms. At this point, let me emphasize the point that at the if this is a cathode and this is an electrolyte, and let's say if you have lithium ions, approaching to the cathode, okay, with the electric field. Then electrons is going to meet the ions to have a reaction like this. This is the reduction reactions. And the neutral lithium is going to be formed at the surface. And then this neutral lithium is going to diffuse inside the cathode according to the Fick's law. That Fick's law is minus d over round x over round c. Okay? So this Warburg impedance should be related to two facts. One is the electrical conduction to make this forms, and the chemical diffusion of lithium inside the cathode, especially this diffusion coefficient. Okay, that is very important to have a good chemical diffusion coefficient. Now, let me discuss about the difference between cathode and anode. Okay. Now, when you have a electrochemical cell, and this side is cathode, okay, and then we have an electrolyte in between, and this is anode. What is the real difference between cathode and anode? Can you answer that? That is the reaction happens. Reduction and oxidation, that is the chemical reaction happens. But physically or chemically, the cathode and anode, the function of the cathode and anode is totally different. Okay? The anode is a sink or source of electroactive species. Is nothing but the sink or source of electroactive species. For example, if you are talking about the lithium batteries, for example, then this anode is just a lithium source or lithium sink. Nothing but just a sink or the source of a lithium. But in the cathode, this is not a sink or source. Cathode is the material which determines the capacity of the batteries of the system. In other words, how much lithium can be contained is going to determine the capacity of the batteries. Okay. Now, according to the Nernst equation, the EMF voltage is minus RT over ZF. Okay, and then log activity of cathode electric active species, okay, and then activity of anode of electroactive species. That is the voltage which determines both in these batteries, right? Now, if this anode is just working as a source or the sink, it just work as a sink or a source, this activity doesn't have to be smaller than 1. Okay, if we use the pure material, then it's going to be 1 to have a good potential here. Right? And so if this battery is working, the electroactive species is the lithium, we better use the lithium metals, and that is the best, right? Because that is going, the activity is going to be the 1. Now, about the cathode, to have a good voltage here, we know the Gibbs phase rule. If this cathode consists of 2 phases, okay, then the change in the activity will not give you any variables, the EMF. So, what we want to have for the cathode is to contain as much electroactive species as possible. That's how we build the cathode materials. So we do not have many choices for the cathodes. For example, in the lithium batteries, in the LMO, LCO, LFP, I think these 3 are main choices we can have for the cathode in the lithium batteries. Why is that? Why other materials cannot be used as a cathode? So you have to think carefully, what is the difference between the anode and the cathode? What is the role of the anode and cathode? Okay, and then you have to understand the Warburg impedance. Why this Warburg impedance is related to the chemical diffusion coefficient of the electroactive species, neutral electroactive species. Now, this is a cathode, and this is x equal to 0 at the surface, which is in contact with the electrolyte. Okay, when you try to insert the electroactive species into the cathode materials, for example, then at certain instances, the concentration is going to be like this. If originally it has some concentration of electroactive species at this level in equilibrium, okay, and then you begin to put some lithium into the cathode electrically, okay, then the electroactive species is going to be set on the surface, x equal to 0, and then take electrons, and then it becomes neutral at the surface. Now the next one is going to be added to the surface and added to the surface until it has some concentration this much, but this concentration of electroactive species will diffuse into the cathode only by chemical diffusion according to the Fick's law. Nothing is working on this. So what is the difference if you have a high diffusion coefficient of electroactive species in a cathode or low electrochemical, no low chemical diffusion coefficient? What is the difference? What is the difference? Who can say this? Is anybody can answer this question? Kim-do, what do you think if you have different chemical diffusion coefficient in your cathode? Now, for instance, if you have a high diffusion coefficient material, then compared to the low diffusion coefficient materials, what is the difference? The only difference is that when you have the concentration pile up at the surface like this, if you have a high diffusion coefficient material, then this one is going to diffuse into your material fast. Now, if this one goes into your material, into your cathode fast or slow, will that affect anything in your system? It will affect in your system because according to the Nernst equation, the voltage is determined by the surface concentration of the electroactive species of the cathode. This is the, you have to remember, this has to be at x equal to 0, at the surface concentration. So if you have this profile, or for instance, if you have this profile in your cathode of an electroactive species, the EMF, the voltage is the same, because at x equal to 0, you have a same amount of electroactive species. Okay? So if you have a high diffusion coefficient, then the low diffusion coefficient material shows this, but if you have a higher diffusion coefficient, then this profile is going to be changed like this. It's going to be changed like this at the same time. I mean, okay, dt square root, this is the diffusion length. So if you have a high diffusion coefficient material, then at the same amount of lithium or electroactive species pile up at the surface electrically, the voltage that you are going to obtain is not going to be decreased much, because the surface concentration goes down instantly because of the high diffusion coefficient. So for the cathode materials, you have to have high diffusion coefficient materials, high diffusion coefficient of electroactive species. Can you see this? Okay? Otherwise, only a little bit of a lithium or electroactive species is going to be passed or inserted in your cathode. It is going to ruin all the voltages, because the surface concentration is not going to be diluted inside your material. But if you have a high diffusion coefficient materials, then a lot of electroactive species are forced to pile up at the surface, inserted in your cathode material, that can be accommodated into your whole body of a cathode through high diffusion coefficients. Okay? So in that case, your battery has a high capacities. Okay? For the cathode, you need to have high diffusion coefficient of electroactive species to have a good batteries, to have a good capacitors, right? But what about the anode? Anode, if you have a, now at the same plot here, now is electrolyte, okay? The anode, electrolyte. Now if you have a certain concentration of electroactive species in anode, like let's have this much of electroactive species. Let's just talk about the lithium batteries, okay? Let's suppose to have an anode with this lithium concentration of this level, Okay, that is obviously not 1. If it is 1, then the activity is 1, then it means that it is a pure lithium metal. Now let's suppose we have some alloys like lithium aluminum or other alloys where the lithium activity is not 1. So it has a certain level of this. Okay? Now if you take out some lithium from here, then the surface concentration of lithium is going to be depleted. Okay? So it's going to go down like this. Okay? As you take out the lithium from this materials, anode. So if it is the activity is not 1 and it is a kind of a compound like this, then the surface lithium concentration is going to be depleted as you proceed to the removal of lithium in the anode. And at certain time, the potential that you measure in your battery is that this and this is going to be, this and this is going to determine the potentials, EMF, there. Okay? Now, if, let's suppose this, at here, lithium is going to be ionized like this, okay? And the lithium plus ion is going to move around in this electrolyte, and then it's going to insert it. It's going to be inserted into the cathode, okay? And this reaction cannot happen. Let's suppose this reaction cannot happen at some certain point. This reaction is not only related to the thermodynamics of lithium aluminum, but also it is related to the kinetics as well. So more dynamics. Even though the potential or the driving force is related to the thermodynamics of this system, the reaction speed or the reaction really can take place or not is determined by the kinetics. Okay? So even though lithium can be ionized like this because of this potential thermodynamics, but the phase formation related, the kinetics cannot allow that. Then this ionization cannot happen. For instance, if you use the graphite for the anode or platinum, which does not contain any lithium at all, we call that blocking electrode, right? If you use that, then there's no source for the lithium. Then what is the EMF is going to be defined? It cannot be defined because we do not have any activities of electroactive species, lithiums at all, according to the Nernst equations, right? So if that is the case, what's happening is that we are going to have a concentration of lithium. We have some concentration of lithium in the electrolyte. Okay, this usually the electrolyte is ionic conductor, only lithium conducting material, so that it just contains a certain amount of lithium in it. Okay, is some diluted materials. So it contains lithium, and then that is going to be the potential is going to be concentrated at a certain layer. We call double layer. Okay, the resistance is so high that all the potential is concentrated at the vicinity at the very close to the anode surface, so that the lithium ion is going to be supplied, and it's going to form some depleted zone, depleted region of lithium ions at the surface of the anode. Okay, if this situation continues for a long time, then this layer is going to be widened as a distance. At the same time, some dissociation of the electrolyte will happen. The gas is going to be formed, the bubble is going to be formed, and any other second phase is going to be formed in the electrolyte. Okay, electrolyte is not going to be stable. But anyway, for instance, if you have a blocking electrode like that, it is not going to be used as a source. But what about the sink? It can work still as a sink. In other words, if the lithium which is contained in the cathode, and then it is going to be ionized at the surface, okay, and that is the charging, we call that the charging process, okay? And then this lithium is going to be attached on this blocking electrode, graphite or the platinum. And what happens? What is the difference in that case? The lithium insertion into this anode or the lithium insertion into this cathode? What is the difference? Lithium insertion into the cathode, we call that is a discharge process. Lithium insertion into the anode, that is going to be called charging. And if there is no difference, then the anode and the cathode should be the same one. Okay? As I told you, the diffusion coefficient of electroactive species in the cathode is very important and is a determining factor of this battery system. What about the diffusion coefficient of lithium in the anode? Will it be a determining factor of the battery system? It's not going to be. Why? Because the neutral lithium, which is formed at the surface, doesn't have to be inserted into the anode materials. Because the anode is just a sink or the source of the lithium. So we don't have to make this lithium inserted into the anode. This lithium just sitting on top of the anode, that's enough. That is going to be called electroplating. Okay? That is going to be, that is electroplating. Electroplating, we have a pure lithium as a thin film on top of the substrate. That is the electroplating. Now, let's suppose we have a platinum or graphite, okay, as an anode. And then we take lithium out from the cathode and put the lithium into the anode. And this platinum and this graphite, cannot accommodate the lithium. In other words, the diffusion coefficient of lithium into these materials is very, very low, let's suppose. And that is really true in the platinum or the graphite. Then the lithium will be accumulated at the surface. And if we have a good adhesion of this lithium to this substrate, then we call that electroplating, and the activity of anode is just like the pure lithium activity is going to be 1. And that is good. Let's suppose if it has a good diffusion coefficient of lithium, so that some of the lithium is going to be diffused into this anode. Let's suppose that, okay, like a cathode. Then at a certain instance, the lithium is going to have a concentration like this, and then the concentration profile is going to look like this, okay? And then if it has a very high diffusion coefficient of lithium, this anode, then this concentration go down and go down. It's going to stay away from 1. Then that is not good for the voltage. That is not good for the batteries. So, for the anode, we do not want high diffusion coefficient of electroactive species. But for the cathode, the diffusion coefficient of electroactive species is very critical. It should have a high diffusion coefficient to have a high potentials for this. Sometimes people working on the anode system to have to accommodate the lithiums, okay? That is, there are many reasons for that. Not just for the capacity, to enhance the capacity. Actually, if you use compounds of lithium alloys like this, instead of a lithium metal, then you have to sacrifice some of the voltages, because this activity here in the nominator is not 1. In a compound, the activity of lithium is not 1. It's less than 1. Okay? So it is going to sacrifice some of the voltages. For instance, if you have a 3 volt as an open circuit voltage, if you change the anode, then open circuit voltage is not going to be 3 anymore. It's going to be less than the 3. But why people working on the developing of new compounds for the anode? Why? Because, for instance, in the case of lithium, if you use a pure lithium, then everything has to be fabricated in the dry box, oxygen-free environment, moisture-free environments. Very costly, okay? But if you use the lithium aluminum, for instance, as a anode, then you can fabricate the batteries in air, because the activity is not 1 in the lithium aluminum, so that it is not that reactive with the oxygen. So people working on the cathode, anode materials other than the pure lithium in a lithium battery system is just because they want to make the production cost low. And they have to pay the voltages. Now, so this Warburg impedance is related to the diffusion coefficient of the electroactive species in your cathode. Not only that, it is also related to the charge transfer resistance, and then we're going to talk about it later. Okay. Now we have 3 cases, and let me just briefly talk about the basic electrodynamics. the resistance and the capacitance is connected in series, then the impedance is going to be represented like this. And then if you make a plot, you are going to have a straight line according to the frequencies that you measure. You know, the current in the capacity is C over dt over dV, right? So the frequency will create the current anyway. So this is going to be the R, and then we are not going to have much information except the value of R if you make a plot like minus x over R. But if you make a plot B over G, okay, then you're going to have a semicircle here. And at this point, this is R, 1 over R. And then we're going to have information about the capacitance here, because the maximum point here is W or frequency, and the capacitance and the resistance is going to be 1 at its maximum point. So we can have information C and R here, and the frequencies is going to move. We're changing experimentally the frequencies from here to here, so we know the maximum frequencies, okay? And then we know the R value here of this semicircle. Then we can determine the capacitance here, okay? And if you have resistance and the capacitance connected in parallel like this, then we're going to have admittance. It's going to be like this, okay? And then in a plot of B over G, then again we're going to have a straight line with respect to the omega like this, so that we do not have much information out of this. But if you plot minus x over R in this case, then now we're going to have a semicircle. Now frequency is now moving from low frequency to high frequencies like this, and then the maximum point here again, this is going to be 1, like this, okay? With this knowledge, we can solve the situation with a blocking electrode where Mx and P, and the connection is now going to be Cg. This is a geometric capacitance, and this is a double layer capacitance due to the polarization, and this is a bulk resistance, including the internal resistance and everything, okay? we can approach this on the basis of this. Okay, Ci is greater than the Cg. Okay. Typically, Ci is 10 to the minus 6 farads per square centimeter, but the Cg is only 10 to the minus 12 farads per centimeter square. And the reason is that, the capacity is something like this, right? Here, the thickness of the geometric capacitance is very large compared to the double layer due to the polarization at the electrolyte at the electrode surface. So the D is tremendously different in between this, so that it has the capacitance is going to show that much difference. Okay. So just intuitively we can see that at low frequencies, okay, then the circuit now RB and Ci here, and this Cg, we are not going to have any current through the Cg. This is the resistance is infinity at the low frequencies, because the current that we're going to have is going to be, see, dV over dt. And in this Cg, this is low and the frequency is low, so that the total current is almost none. Okay? So at low frequencies, the total whole circuit is going to be simulated as the series connection of capacitance and the resistance. And at the high frequencies, on the other hand, the whole circuit is going to be simulated to Cg here, because Ci is shorted. See, this is too high, and this is high again. So we have a large current here through this Ci at the high frequencies, so that we can regard this Ci as a shorted. Okay, so then the whole circuit is going to be changed to the parallel connection of resistance and the capacitance. So if you make a whole spectrum from low frequency to high frequency, then we can, from the formal knowledge, we can make a plot X versus R, or we can make a plot B versus G. Okay? And if you make a X versus R at the low frequencies in a series connection, we know it's going to have a straight line in X and R. Okay? At low frequencies. So low frequencies start, we change the frequencies from low to high, and then you're going to a straight line, and then the point here is going to be corresponding to the R, also B. Okay, and then if you increase the frequencies further, then it'll move like this, and the maximum point here is going to be omega Cg Rb is equal to 1. We cannot have any information about the Ci, the double layer capacitor thing. But if you make a plot like this, then low frequencies, we're going to have a semicircle, and at the high frequencies, it is going to be parallelly connected, and from formal knowledge, you're going to show the straight line like this, okay? If you make a B or G. And then the maximum point here is now corresponding to Ci Rb equal to 1 here. And then here is going to be Rb, 1 over Rb, the point here. So we can have information about the Ci with this plot, and then Cg with this plot, and then we can separate out the bulk resistance. So if you make a spectrum changing the frequencies from low to high in that blocking electrode system, okay, in this blocking electrode system, then you're going to have this profile and this profile, and from this you can determine the values corresponding to the bulk resistance and the double layer capacitance and geometric capacitance separately. This is beautiful, isn't it? The blocking electrode M, Mx, and P, this electrochemical cell can be simulated into resistance Rb and capacitance Ci, and then Cg. It can be simulated with this. The whole reaction can be simulated to the electrical circuit like this, and then for each reaction we can separate the values, and that is the beauty of this AC impedance spectrum. Okay, let me pick up from here and then finish the AC impedance spectrum, and then next week on Monday. And on Wednesday, probably we're going to talk about the fast ionic conductors, the new chapter. Okay.